connection. Okay, perfect. So, as I promised, today we will discuss what's happened at the webinar, what's happened with cola. Typically on my table in webinar time I have water bottles, I have Coca-Cola bottles, and we will discuss pH questions. So, and I show main principle, how to solve. At first, what we will start, it's about definitions. Ka, pKa, and pOH. It's what you must to know. K, it's constant. Literally, it's mean mathematical ratio between product and reagent. For example, we have weak acid. My favorite weak acid is hydrochloric acid because it's small and easy to balance in. As any weak acid, it's reversible, dissociate into two particles, H plus and F minus. And mathematical ratio for constant will be K equal concentration of H plus times concentration of F minus divided by concentration of HF. Square brackets in chemistry using a symbol of equilibrium concentration. So, CH plus, it's equilibrium concentration of H plus. We also very often dealing with Ka. Ka meaning acidic. So if you see A, it means you're dealing with acid. But sometimes acid very slow. For example, it can be for any weak acid, equilibrium shifted to left, and for any acid, constant of equilibrium will be something like 0.000. It's not very useful. So for making more comfortable writing this constant, chemists use value which mean pKa. pKa, it's minus log of 10 Ka, and K meaning P meaning power. And another P function what we very often use, it's pH. pH it's minus log concentration of H. In different application, in different branches of chemistry, we also sometimes use symbol P, something, P of something, it's meaning minus 10 logs of any function. So it's universal way, and it's what you must recognize, constant of acidity, pH, pKa. So next, what you must memorize, it's Henderson-Hasselbalch equation. For example, it's very precisely very easy describe buffers. And equation itself quite simple. Henderson-Hasselbalch equation, most complicated part of Henderson-Hasselbalch equation, it's name of this equation, because it's pH, it's pKa plus log 10 of base divided by acid. For example, if we're dealing with HF, it's reversibly dissociate into H plus F minus. And if we're dealing with any salt of weak acid, for example, soluble salt, it's reversible dissociate, it will be Na plus F minus. So if we're dealing with mixture of acid and salt of weak acid, or if we're dealing with base and salt of weak base, we can use Henderson-Hasselbalch equation for quick calculation. What's interesting about this equation is because if ratio of acid and conjugated base same, log of 1 equals 0, and pH of salt of weak acid and pH salt of weak base with conjugated acid and base will be equal pKa. So if concentration of fluorine minus equal concentration of HF, pH will be exactly as pKa. And it's even if you don't, if you forget Henderson-Hasselbalch equation, what's very important, pH equal pKa if concentration of weak acid equal with concentration of conjugate base. And now we will discuss, as I promised, especially who watch Reddit or my groups, phosphoric acid, it's weak acid with 3 pKa. In my stomach, pH even less than 2 because I am a little bit hungry. Intestines can be different because sometimes you eat, sometimes you not eat. Sometimes you're hungry, sometimes you're not hungry. But in your blood, pH always same. pH 7.4 because it's very important. And urine also pH from 5 to 8. Interesting fact, but if you eat a lot of meat, your urine will be acidic, a little bit acidic, close to 5. If you eat meat only whole day, your urine will be close to 5. But if you all day eat mainly vegetables, your urine will be close to 8. So you can check any person diet by control pH. But typically pH not controlling in urine analysis, I think so, but maybe not. So what we have here? In stomach we have pH 2 and we have 2.2 closest pKa. It means if pH will be equal 2.2, concentration of first step dissociation acid will be same. Phosphoric acid dissociate into 3 steps: H3, pO4, reversible, H2, pO4 minus plus H plus. It's first step. And concentration of these 2 molecules will be same if pH will be equal 2.2. But we have less. Its main form for phosphoric acid in stomach will be this phosphoric acid itself. Second, about our blood. Same situation, but in this case we dissociate phosphoric acid more deeply. NH2O. I always try to write sulfuric acid because it's my favorite acid, because it's produced in my native town in big amount. And so let's discuss and next step, three steps. And last steps, I think enough. Equilibrium pH will be 2.2, and here equilibrium pH equal 7.2. In blood we have 7.4. So it's close to case when these molecules, these ions and these ions with equal concentration close, but because pH little bit higher than constant than second equilibrium constant for this equilibrium, it means it's major form H. But if we compare with previous one, it will be not 99%, even not 90%. It's something about 80%. So H2PO4 minus concentration also high in our blood. And if you see, if you probably know, pH of blood also can be differ, but not so differ as urine, not so differ as stomach pH. It can be sometimes 7.35, 7.37. So changing will be very small because what inside our body concentration, it's very important. So in our blood, main form of phosphoric acid, in my blood, for example, do you remember a couple minutes ago I drink a half cup of cola. So part of this cola now in my blood and existed in HPO42 minus, its major form. And what next? What's happened with my phosphoric acid after lessons? After lessons, maybe in 2-3 hours, water will leave my body and will be trapped by toilet water. And in toilet water, pH equal 8. So, like in previous case, constant of equilibrium second stage, it will be PO4 minus reversibly dissociate into HPO4 minus plus H plus, and major form will be equilibrium will be at 7.2, but we have 8, so major form will be same. So most popular phosphoric acid ions in blood, in intestines, in urine, it's HPO42 minus, and actually it's phosphoric acid. It's one of major buffers in our blood. Okay. So let's solve more complicated about pKa. It's more complicated because we need to use Henderson-Hasselbalch equation, and here no answer, but principle same. At the 3.3 will be equilibrium, but we haven't. So we must use Henderson-Hasselbalch equation. pH equal pKa plus log base divided by acid, and 1.6 equal 3.3 plus log A minus divided by HA. So for solving this problem, we need calculator. So 1.16 minus 3.3 minus 1.3 equal log A minus okay, and 10 power ratio A minus divided by HA. Oh, how I get it? This ratio A minus divided by HA equal 10 power minus 1.7, and it will be equal 0.02. So mainly at the inside stomach, mainly aspirin exists in not dissociated form. Let's make same for blood. pH equal pKa plus log A minus divided by HA, and again pH equal 7.4, pKa equal 3.3 plus A minus HA, and again 4.1 equal log A minus divided by HA. So ratio anions, it doesn't matter how anions look like, divided by concentration of acid equal 10 power 4.1. So it will be 30,000. So mainly inside our blood, aspirin exists by more than 99.9% in anions form. So it's all what you need to solve questions like this. So if we generalize, what you must memorize? K, it's constant. As any constant, it's product divided reagent. Ka, it's mean constant of acidics. If you're dealing with acid, it's constant. It's literally constant of acidic dissociation. pKa, it's minus log 10 of Ka. pH, it's minus log 10 of H. And sometimes you need to know Henderson-Hasselbalch equation. Equation itself quite simple, but name it's very hard. So it's all what you need to know for questions like this. For today, I finishing, and thank you for watch my webinar. We will continue solve pH questions at this Wednesday and Friday. So thank you for watching, subscribe, share, and visit my streams. Bye.